Good day, class. For today's discussion, we will be talking about performing mensuration and calculations. To begin with, let us all be familiarized first with some of the definition of terms. So the first term, we have bit. A bit is a fundamental unit of information having just two possible values. So what are those possible values? It's either number 0 or 1. For the next term, we have byte. A byte is a unit of digital information in computing and in telecommunications that is mostly consist of 8 bits. Okay, again, for bit, it's either number 0 and 1 or 1, while for byte, it consists of 8 bits. And for the last term, I know you are very familiar with this. So the term is booting. Booting happens when we start up our computer wherein it loads the operating system from the disk. So can you give some examples of operating systems? Okay, very good. Some examples of these are Windows, Windows 7, Windows 8, Windows 10, and many more. Moving on now to the digital representation, always remember that in computer, information is represented and stored in a digital binary format. So later on, we will talk deeper about this digital binary format. Okay, talking about bit again, a bit is the abbreviation of the word binary digit. So this bit represents the smallest piece of data when we are talking about computers. Okay, look at this representation. We humans interpret words and pictures. The moment we see pictures or words, so our brain will process that information. While in computers, our computer interprets only the pattern of bits. So how does it happen? So the computer has the system unit or the central processing unit rather. Then through that central processing unit, the pattern of bits will be processed. So as we talked about earlier, diba, bits refers to either 0 or 1. Okay, this is how a computer interprets bits. Okay, looking at the picture, you can see two numbers there, which is numbers 1 and 0, which refers to the, bit. Because bit is either 1 or 0. Talking deeply about bit, it can be used to represent the state of something that has two states. So one good example of this is a light switch, because light switch can either be on or off. So in binary representation, these states corresponds to 1 and 0. So 1 for on or off. Okay, very good. 1 for on and 0 for off. Diba? As you notice, when you see switch, you can see there's a representation of 1 and 0, just like this example. Okay, like this. So it represents, number 1 represents the on and number 2 represents the off. So for this side, it is off since the light is switched to 0, and when the light is switched to 1, so then it will light on. So there are some examples or possibilities that 1 and 0 is combined. So this is what you will see. This is represented like this. So this means that the switch can be used for turning on and turning off the device. Just like this. So one single button for on and off. And another one. This is for 1, which means on, and 0 for off. Computers use binary codes to represent and interpret letters, so numbers, special characters with bits. So the common used code is the American Standard Code for Information, which is commonly known also as Ascii Code. So to give you an example, so computers understand the letter A as this code. So the code is 01000001, and for example, it is a number. The computer will interpret that number 9. So we humans interpret this as number 9. So we understand this as number 9. But computers will interpret this number as 00001001. And if, for example, this is a special character, the computer will interpret this as 001000001. Okay, each group of 8 bits, such as representations of letters and numbers, is known as bytes. So this is already mentioned earlier. So this is an example. So let us count how many bits is this. 1, 2, 3, 4, 5, 6, 7, and 8. So this is 8 bits, wherein that 8 bits is equivalent to 1 byte. Okay, for you to understand it more, so we have here 1, 2, 3, 4, 5, 6, 7, 8. So this is equivalent to how many bytes? Okay, 1 byte. And another 1, 2, 3, 4, 5, 6, 7, 8. This is equivalent to how many bytes? Okay, very good. Another byte. So 1 byte plus 1 byte, that is equivalent to 2 bytes. Okay, now that we really understand bits, let us now move on to converting decimal to binary numbers. So, talking about decimal numbers, these are numbers that has base 10, which it includes numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Again, the base is 10. While for binary numbers, you already know this, that it's either number 0 or 1. So the base for this is base 2. You should remember this. Okay, moving on to the step in converting decimal numbers to binary numbers, the first thing that we should remember is to divide the number by 2. So the operation that we are going to use is, okay, division. And there is a value here given, so we need to divide it by 2. For the second step, get the quotient and the remainder. Of course, when we are dividing the number, we are focusing on the quotient and the remainder. For the third step, you need to bring down the quotient divided by 2 and get the quotient and remainder again. So we're going to do this step repeatedly until the quotient results to, okay, very good. We should take note of this, so we will just stop dividing it until we get the result 0. And we should copy the remainder from bottom to top, and that will be the binary equivalent of our decimal number. So I just want to emphasize here that in converting decimal to binary numbers, we will focus here in the remainder, because the remainder will be the binary equivalent of our decimal numbers. Okay, let's have an example. For example, we have this decimal number 15. So in this example, our decimal number is 15. Again, what is the base number for decimal numbers? Okay, very good. Don't forget to write the base number, which is 10. So let's try dividing it. So the usual way, this is how we divide a number. 15 divided by 2. So 15 divided by 2, that is 7. Very good. 7 times 2, that will be, okay, 14. So we need to subtract this. So don't forget to put the point there. So 15 minus 1, that is 1. So let's add 0, bring down 0. 10 divided by 2, that is, very good, that is 5. Multiply it by 2, and that will be 10. So this is the way how we divide a number. But in getting or in converting decimal to binary numbers, we will use different way in dividing. Okay, for you to be able to get the binary equivalent easily. Okay, are you ready? Okay, let's start. So again, the decimal number is 15. So let's write 15 here. So this is how I'm going to divide this. 15 divided by what value? Okay, very good. The value is 2. So 15 divided by 2, still this is 7. As what I have mentioned earlier, the most important here is the remainder. So we are going to write here the remainder. So take note, when we are dividing here, if there is a remainder, we're going to represent the remainder as number 1. So whatever the remainder is, as much as there is a remainder, we're going to represent this as 1. And if there's no such remainder, we're going to write this as, okay, very good, 0. So this will represent the binary. It's either 1 or 0. Okay, let's continue. So 15 divided by 2, that is 7. So is there a remainder? Okay, very good. There's a remainder. So I'm going to write what number here? Okay, I'm going to write 1. It is said there that we will just stop dividing if the value is already 0. So looking at this, it's still not 0. So we will continue to divide it. 7 divided by the same value, that is 2. That will be, what's the answer? Okay, 3. So is there a remainder? Yes, of course, there's a remainder. 3 times 2 is only 6. So there's a remainder. Continue dividing. 3 divided by 2. Okay, what will be the answer? Very good, that's 1. So is there any remainder? Yes, there's a remainder. So let's put 1 here. And still, we need to divide it by 2 because it's still 1 and it's not 0. So 1 divided by 2, that is 0.5. So since it is not exact 0, so we're going to put 1 here. Okay, do we still need to divide it with 2? Okay, we no longer divide it with 2. So now, looking at this side, this is the binary equivalent of our decimal number 15. Based on our steps earlier, we need to write this from bottom to top. So now, can you dictate to me what is the binary equivalent of decimal 15? Okay, 1, 1, 1, and 1. Okay, very good. But let us not forget the base number of binary number, which is number, okay, 2. This is how are we going to convert decimal number to binary. So decimal 15 is equivalent to 1, 1, 1, and 1. Okay, is that clear? So another example.
Moving on to another example, we have this decimal number 28. Again, what is the base? Okay, very good, 10. So let us get the binary equivalent of this decimal number 28. So we're going to divide this 28 divided by 2. Okay, what's the answer? Very good, 14. Is there any remainder? Okay, since there's no remainder, what are we going to write here? Okay, very good. So we're going to write 0 because there's no such remainder. Okay, continue dividing. 14 divided by 2, that is 7. Any remainder? None. Very good. What am I going to write here? Okay, 0. Divided by 2. 7 divided by 2, that is 3. Very good. Any remainder? Yes, there is. So I'm going to write what number here? Okay, 1. Divided by 2. 3 divided by 2 is 1. Very good. Remainder? Yes. So I'm going to write what number? Okay, 1. 1 divided by 2, that is... Okay, now we are going to write these remainders from bottom to top. And this will be the binary equivalent. So can you dictate to me the binary equivalent? Okay, first we have 1, 1, 1, 0, 0 with the base number 2.
Okay, so the binary equivalent of the decimal number 28 is 11100. Okay, did you understand how to convert decimal to binary numbers? Okay, this is just the first method. So now I'm going to teach you how to convert decimal to binary number in an easier way. Okay, so in this first method, we use the mathematical operation, which is division. So now we are going to use a mathematical operation which is just addition. Okay, how are you going to do that? So you're going to do that by just using this equivalent. So try to look at the table. So this is what we call as equivalent. So how are you going to get the equivalence? So you are just going to double the number, just like this number 1. So when you double 1, that will be 2. When you double 2, that will be 4. And when you double 4, that will be 8. So what are we going to do with this equivalent? So let us just look at the decimal number. So don't forget to write the base here. So our decimal number is 15. So looking at the equivalence, you just need to add this equivalence, wherein when you add that equivalent, that will be equal to the decimal number. Okay, let's try to do this. So for example, 8. Okay, so what is still missing for us to be able to get 15? So 8 plus, let's try adding 4. 8 plus 4, that will be, okay, 12. So we need more 3. So we're going to write 1 here. 12 plus 2, that is 14. So there's still one missing value, so we're going to write 1 here. So if we're going to add all of these equivalents, then we are going to get 15, which is equivalent also to this decimal number. So the binary equivalent will be 1, 1, 1, 1. So with the base 2. If we're going to look at our earlier example, it's just the same value, and still we are able to get the same equivalent, which is 1, 1, 1, 1. Okay, did you understand? Okay, if yes, let's try another example. So what if our decimal number is 37? So let's try to get what is the binary equivalent of this 37. As you can see, we have here another equivalent. So we need, what we're going to do is just add equivalent. So 16, we double it, so that will be 32. So if it's still insufficient, we will just double the equivalent, then that will be 64. So with this example, since it is just 37, so we will just going to use 32. Okay, let's try to put 1 here, 32. So what is still missing for us to be able to get 37? So if we are going to add 32 plus 16, so that will be it, that will exceed 37. So we are just going to write what number here? 1 or 0? Okay, very good. That will be 0. So what about 32 plus 8? Okay, it will exceed 37, so we're going to write 0 here. 32 plus 4? Okay, that is 36. Very good. So should we write 1 here? Yes, of course. What about, so we already have 36, so if we are going to add 2, that will be 38. So it will exceed 37. So what are we going to write here? Okay, very good. That will be 0. And for this, since 1 is missing, so we are going to write 1 here. Again, let's try to add 32. 2 plus 4, that will be 36. And plus 1, that will be 37, which is equivalent here. Okay, so can you dictate to me the binary equivalent of 37? Okay, very good. 1, 0, 0, 1, 0, and 1 with the base number 2. Okay, 37 is equivalent to 1, 0, 0, 1, 0, 1. Okay, is that clear? Okay, I hope you really understand our lesson, which is all about binary numbers or converting decimal numbers to binary numbers.